Hello, Physics 150. This is Dr. Dave. I wanted to address one of the homework problems that a lot of people were having a lot of difficulty with, and that's specifically problem number 9. Many students looked at this problem and just really got hung up on the language, what they were being asked to do. It didn't look like anything they had remembered before, and so they really struggled. So I wanted to go over it now to make sure everyone had a chance to understand what it is we were looking for. However, in doing so, I have to provide the following caveat or warning. Students get a false sense of security when they read our solutions. They get a false sense of security when they see us do something. They say, oh, that makes sense. And then they don't really think about it again. And the next time they see a problem like it, they're really lost and they don't know how to start. I really want to try to impress upon you, the person watching this video, that what I'm doing is about the process and not the solution. An analogy I came up with today was if you've ever done a Sudoku puzzle, trying to remember the solution to the last puzzle doesn't help you with this puzzle. It's about the process. How did you approach the problem? So what did we have here? We had a trajectory. Trajectory just means the path that an object took. The trajectory of a particle that was launched. And the first question we asked you, does the particle follow a circular path? Hopefully that's a pretty easy answer. No, it's a parabolic path. So why did we ask the question? Well, many people say, oh, circular motion. It has to be a circle to do the following things we're going to look at. And the answer is no. Some of the elements of circular motion can be exhibited in other ways, as we're showing in this problem. So the next question we ask, at what points, if any, is the acceleration only centripetal? Well, the acceleration the object experiences is shown here in red. What does centripetal mean? Centripetal means perpendicular to the trajectory and towards the center of the arc or center of the curve. Well, if you look at this, none of these accelerations are perpendicular. What do I mean by that, right? They have to be perpendicular to the path. So that's not perpendicular, that's not perpendicular, that's not perpendicular, that's not perpendicular. Only one of these is. And so to be a little bit more careful, what do I mean by perpendicular? I mean perpendicular to the velocity, the tangent. So if I look at the velocity at these different routes, I can very quickly see that's not perpendicular. Now I haven't drawn those velocity vectors to scale. I'm simply trying to give a sense of what that perpendicularness is. So the only place that this is perpendicular is at the top. So at what points, if any, is the acceleration only centripetal? At the top point. The next question is, at what point, if any, is the acceleration only tangential? Well, now we have to go to the word tangential, right? Tangential means along this tangent line, right? Well, what would be true if acceleration was tangential? If this is some velocity vector, and this is the acceleration vector, I'm meaning to draw those two as being parallel, then my object would speed up. If this were my velocity vector and that were my acceleration vector, then my velocity would slow, or my speed would slow down. So this is speeding up, this is slowing down. But what you see in either of these two cases is that the object is not changing direction. Tangential acceleration is the acceleration from chapter 1 and chapter 2. It speeds us up or it slows us down. It does not turn our direction. So our question is, at any point along here that we've indicated, is the acceleration in the same direction of velocity or in the opposite direction of velocity? And we see that that's never true, right? The velocity vectors are always at some kind of an angle. So at no point is the object only speeding up or slowing down. So at what points is the acceleration only tangential? None. At what points, is any, does the acceleration contain both centripetal and tangential components? Well, now it starts to get a little bit more interesting. And this is where we have to break the acceleration vector into components. So we have a tangential direction at each point that, right, is tangent to the curve. That is the direction of tangential acceleration. So that means that I'm going to take now this acceleration vector here and split it into components. One of those components is going to be perpendicular to the motion, right? So my motion is traveling this way, perpendicular is that way, tangent is along that direction. There is my A centripetal. Here is my A tangential. And that is now broken up with the right angle being here. We're now going to go to the next spot, and we recognize that this is my tangential direction. That is perpendicular to it. So here we go again. This is A centripetal, and this is A tangential. Make sure we erase those little overhangs and the vectors aren't drawn too long. We get to the next spot. Again, this is my tangential, and that's my perpendicular. And here what we see is that all of our acceleration is centripetal. This is a very boring triangle where there's just two lines at angle of 0 degrees. So in that case, acceleration only centripetal. We kind of knew that already. The next spot we get to is here, right? There's my tangential direction. Here is my perpendicular direction. So this is my centripetal acceleration, and this is my tangential acceleration. Finally, I get to this spot here. That's my tangential. There's my perpendicular. So this is A tan. That's A centripetal. So at each point in the figure, draw a vector corresponding to the total acceleration, a vector corresponding to the centripetal acceleration, and a vector corresponding to the tangential acceleration. We are done with part E. Part F says if the centripetal acceleration if AC is centripetal acceleration and AT is tangential, what is the magnitude of the acceleration in terms of AC and AT? How is the magnitude related to G? And is the magnitude the same at all points? So the question is, how do these components relate to G, or the total acceleration? Well, you learned this a long time ago in Pythagorean theorem. This is your standard triangle, A, B, C. So what do we see here? We see that the acceleration is equal to G, which is equal to the square root of AT squared plus AC squared, right? And this, of course, comes from A squared plus B squared is C squared. So that is our relationship at each one of these points where A equals G is uniform. It's the same throughout. I hope this clarifies question number 9. We're never trying to trick you. We're never trying to make the problem harder than it needs to be. I recognize that it may not always look as familiar as you want it to be. Please continue to ask us questions and continue to reach out. If you got this problem entirely wrong, that's fine. Look at it now, try to redo it, try to fix it. We're trying to give credit for earnest effort on finishing the problems. Reach out with any questions or concerns that you have. Thank you.